Now that we covered the basics of convolution, let's take some time now to just go over a very simple CNN using PyTorch for MNIST image classification. So first thing that we're going to do is, just like last time, we're going to import the necessary libraries and packages that we need. So we'll go through that. And now these are some of the Torch packages that we'll be using. I guess some unique packages that we didn't really cover in our last lesson that we're using now, specifically Torch Vision. So this gives us access to a lot of image data sets, things like being able to transform those images. And then later on, we'll see even ready-made, fully functional models that we can use that have already been pre-trained. So we'll go ahead and load those as well. And let's start by quickly talking about what the whole pipeline is going to look like. So we're going to start with our input, which happens to be, let's say, a batch of images. And we're going to feed that into a convolutional layer. That's going to go through, we're going to have filters convolving through our image, and we're going to get an output. We're going to apply a nonlinearity, which is going to be the rectified linear unit here. And then we're going to apply max pooling. Now this series of convolution, nonlinearity, and pooling, we actually repeat this several times within our simple example here, but we can do this many times. And then the output of this is going to be passed on to a fully connected layer, which we can then use to actually classify our image. So let's start by setting just a few parameters. So I'm going to use a batch size of 64. And then we'll just run it for 3 epochs. I just want to show you, what the training looks like. And you see, you get to really see the power of convolutional networks here. Even with just 3 epochs, you'll see, we reach about, I think, above 96% accuracy. We're going to choose, learning rate, dropout, number of hidden units. We'll try to keep our model small, just to see the power of, again, parameter sharing. And we're going to also use, if you have a GPU on your machine, this will be running just fine. And then we're going to apply the seed as well, so we can sort of reproduce the results that we're getting. So we're going to go ahead and run those. Now, the first thing I want to show is under the utilities, one of the utilities with Torch is the data loader. So this is a very efficient way to sort of load your data and get it ready for training, validation testing, whatever it is. And we have the data sets from the Torch Vision package, which gives us access to the MNIST library. So this gives us all the MNIST images, which are basically just 28 by 28 images, and they're black and white, so it's 28 by 28 by 1. And we're going to load those, and you can see here we actually do some transformations. So things like normalizing the images, we're going to convert it to a tensor, so then these are primed and ready to go for training. And for data loader, you're just going to also specify the batch size, so then all of that's taken care of for you. Now before we start doing any modeling, I just want to quickly visualize. So we're going to load a few examples from the test loader, and you'll see, these are just a few examples. So 64196. It's black and white, but we use different coloring here so you can really see the numbers. So the objective is to read all the pixels in each image, and then we're going to classify what number is being shown. So the first real model component is this CNN class, and within the class there are 2 main components. First is actually initializing everything that we want for the model. So first is a very simple convolutional layer. It's going to be a 2D convolutional layer, and what these numbers mean, basically 1 is the number of input channels. So like I said before, the images are black and white, so there's only one channel. If we have images with color, that's going to be 3 channels, RGB. Now the next number is 10, which means that's how many output channels we want. And the last parameter here is kernel size, which is 5, which means our filters are going to be 5 by 5s. We're going to do another convolutional step, so we're going to go ahead and define that filter as well. That's going to be a 10 input channels, because we're going to receive the input from the previous convolutional step. We're going to output 20, and then again, same kernel size. We're going to use dropout after the second convolutional step, just so we can avoid things like overfitting and we'll get a bit more of a robust model. And then we'll finally take that output from convolution into our fully connected layers. And I'm going to talk about where we get the 320 and things like that. We'll go through the shapes so we can understand how the image shape is changing as we go through the convolutional layers. Let's go ahead and do that right now, actually. So once we initialize all this, The forward will basically take in a batch of images and it'll explain what's happening to that batch, and then we're going to see the output, which is going to tell us what class it's going to be. So the first step is you'll see it's self.conv1 of the input image x. When the image is first coming in, it's going to be the batch size, which is 64, and 28 by 28 by 1. So after we apply the first convolutional filter, we're going to receive a size of 64 by 10 by 24 by 24. Now these sizes may seem a bit arbitrary, but that actually is the output based on what filters we used. And these are just simple equations that you can use to basically do a little sanity check for yourself to see what the output shapes should be. But you can also even visualize this spatially or draw it out on paper, and you can see if you actually take the filter and convolve it through the images, this is the output shape that you're going to retrieve. So after the first convolutional step, basically it's very simple. You're going to take the width of your image, subtract the filter size from it, and you're going to add any padding that's in there. And then if you divide that by your stride, basically the stride of the filter moving, convolving across the image, and then you're going to add 1 to that, and that'll give you the new dimensions. After convolution, you apply your nonlinearity, which is right over here. Before that, you're going to do a pooling step, which is going to basically reduce reduce the dimensionality of our image. So pooling here, we just do a simple max pooling, two-dimensional max pooling. So this is, again, another simple equation you can use, and the output of this is going to be 12. So we just reduced our image from the original 28 by 28 to this 12 by 12, but it has 10 channels now instead of 1. And we're going to repeat this for another convolutional layer, and we'll talk later about why we want to use multiple convolutional layers. And then after the second pooling step, we're going to receive basically a 4 by 4 representation with 20 channels. And now we're ready to feed this into our fully connected layer. Now before you feed it in, you have to flatten it because that's how fully connected layers work. And this is where we get that 320 that I mentioned earlier. It's the 20 multiplied by 4 by 4. So we just flattened our feature maps into this nice flat response that we can feed into the fully connected layer. So now we are ready to start training this. Now that we know, how the data is actually being manipulated. So the first thing is we're going to say our model is the CNN that we just went over. We're going to use the atom optimizer, and our criterion is going to be cross entropy loss, because we're basically trying to predict which classes it is, and that'll work for any categorical type of tasks. Now you can go ahead and experiment with different types of optimizers and things like that, but we'll go ahead and stick with this. Now these are the same utility functions from our last lesson. This one is to process a batch, basically just take our batch of images, go through it. We're gonna, if it's for training, we're going to propagate our images through our network, get the loss, feed that back through the network, and then adjust the weights accordingly so our performance becomes better. And now let's go ahead and train this model. Now while it's training, I just want to maybe point out a few key things within the training module. We're going to do training and validation. That's why you see a lot of this code. And it's sort of important to do validation, especially when your models get deeper, because training performance may look great, but then when you want to do it on a new test set or something like that, it may not perform so well. So that's what all this code is for. And then we have a little verbose statement so we can actually see the performance after each epoch. Now you see here, we're running on the GPU, and just 30 seconds for 3 epochs, and the performance is already close to 96%. And you can go ahead and try this with traditional feed-forward network without any convolution, and the performance is not going to be anywhere near this. So it's almost done training, and we will see, there it is. Last epoch, we are 96.5% test accuracy, which is fantastic. Now, once you have your model trained, we can do some pretty cool things. We can do some inference. So let's go ahead and see, maybe for some images in our test set, let's see what the image actually looks like, what the class is, and then what we're saying the class is. So this is for inference, where we're just going to just do the forward pass and get the class. We'll go ahead and view our images again, and you'll see here 04876, and looks like all of our predictions match up. So our model looks pretty good here. So we can do some really cool things. You can try to predict, maybe some weird looking numbers, or try to see which numbers have the highest performance, things like that. So that's pretty cool. So you just saw, how quickly we created this model and how simple it is to do with PyTorch. We don't have to worry about a lot of the internal mechanisms here. And now for the next section, we're going to, basically first Alf's going to talk about some of the really popular models and CNN architectures that are out there for image processing, and actually a variety of different tasks. And then we'll cover, how we can use this within PyTorch, because they already have all these pre-trained built-in models and data sets that we can use for whatever it is that we're trying to create.